Let's go live. Can everybody see it?
Yes, sir.
Yes, good point. Block 7 resources in Discord or CTS Wireless for the appraisals. Either way.
How many are on the test again? 40?
Yep. 40 questions. You can only miss... Oh, good. He did send it to me. 40 questions. You can only miss 12. In other words, you get 28 correct, you're good to go. You pass the test. I don't recommend that you try to miss 12 because there's always that human error. Now, one of the things when I'm there at the testing lab, I tell you to do a couple things. The first thing is I tell you to take your pencil and line through 1 through 41 all of the echoes. In other words, you're developing a box. I've had students where they will answer echo, and some instructors will not give you the benefit of doubt and tell you, hand the paper back to you and say you might want to check this. But it just gives you an idea that if you're checking an echo and there's a line all the way through it, you're going, I think I screwed up on that one. And also, if you line through 41 to give you that, hey, I got answers A, B, C, D, from 1 to 40, I have seen this happen where people accidentally skip and they're answering 41. So those are my tips when you go take this test on Tuesday. Just suggestions. I think Sergeant Norden will be your testing proctor, so to speak. All right, so everybody can see me? Everybody can see the slideshow? Ready to go?
Yes, sir.
Okay. So, let's, we're missing Robinson. 1, 2, 3, 4, 5, 6, 7. Yeah, we're missing Robinson.
Wait, do we test on Monday or Tuesday?
Tuesday. The last time I took a look, Tuesday.
Wait, today is day 5, correct? Or yes, day 5.
You have lab tomorrow, lab Monday, and lab Tuesday, but the test is also Tuesday. So whatever you don't finish up as far as labs are concerned, you'll be doing in the afternoon. But since there's only 8 of you, very interesting. Is that what has it on your sheet there?
What about Friday? Or am
it's
I
a down
missing
day.
something? Oh, really?
Yes.
Oh, I'm off then.
That's fine. I had to relook at the schedule several times for this week. It's just a 3-day work week, which is lovely. So now we're back on schedule as far as the way the down days are.
Oh, okay, that makes sense because we had it last week as well. It kind of that's the confusing part. All right,
it was one of those 4-day weekends followed by a 3-day work week, and you have a 3-day weekend. They purposely did that so you could have a long holiday weekend as well as following it up with a 3-day work week and a 3-day weekend.
Okay. Thank you for clearing that up.
Sure. Hey, I'll be the first one to tell you. I get confused at times too with the stuff. All right, so we're going to look at the transmit path, the receive path, the standby loopback, and the Orderwire. All this is in your C's and D's. If you wanted to take a look at them, you can. Now, one of the things that I have found out, a lot of people get confused with the circulator, duplexer, and diplexer. So what I did is I went online and found these devices. All right, a circulator. It gives you an idea of what a circulator does. It's kind of crazy how it does it, but in our case, it's a 3-way. You will have RF that will be going, in our case, you're going to have an incoming and outgoing path on number 2. 1 could be the transmit side, 3 is the receive side. So number 2 is where that input output is. Inside of that circulator there is basically a connection, and they have ferrite cores that know that when the receive is coming in, it will route the receive and prevent the transmit from going in. And same with the transmit, it will prevent the receive going in, but let the transmit go out, all on number 2. 2 is an input output. Next up, we have Duplexer. This is that bidirectional on one line. You're going to see it on the 2-foot cable or the 150-foot cable. So I encourage you, when you get ready to pull that 2-foot cable out, look at both ends. You'll see one piece on there that will give you an indication that, wow, this is an RF cable. It's pretty small, but it's an RF cable. That is where the duplexer works off of. It's a two-way street on that cable. What is the differences? If you take a look at this VHF UHF indoor duplexer on this screen here, you will notice that it has on looks like the left side, it has 1.3. Maybe I'm looking at it incorrectly, but it looks like 1.3 to 225 megahertz, and on the other side it says 350 to 540 megahertz. So what that's telling you is that is its input output. The one where it says COM, that's the common one. That's what's going to go between the two different duplexers. And we're going to see this in the TISR. And next up, we have a diplexer. This is basically another way of being able to take the signals and separate them out or put them together on one. You can see on one side we have the antenna, which is the over-the-air antennas, and this is your SATCOM guide input or output. I have used these before. I've not used these. Okay, so they pretty much work similar, but this is where things get a little crazy because your antenna here, the over-the-air antenna, is anywhere between 200 and 800 megahertz versus your SATCOM, which can be higher. So I just wanted to point that out, the differences between a duplexer, a diplexer. Again, these are passive devices along with your circulator. There are pictures on Google of a circulator, but they all work kind of similar. Circulator only 3 points. You have your duplexer and your diplexers the same way. It depends on what they are going to do. So we're going to look at the baseband assembly. And if you pull up your set of schematics, let me click on this one and move it out of the way. That's not what I wanted to do, but this part right here is on the rear of the baseband assembly. This comes or goes to your multiplexer. The first thing it hits is an attenuator. You'll notice it says 30 dB of attenuation on your steps, and that is because you do not know where or what kind of voltage is coming out of that multiplexer. For example, if that multiplexer was 3/10 down the road a piece on a 200-foot cable and coming in, it's going to be pretty weak signal, so you're not going to have to attenuate 30 dB. You're probably going to have to attenuate maybe 2 or 3 dB. But if your multiplexer sits right next to the baseband assembly, more than likely you're going to have to use that attenuator. There are 2 items on that attenuator switch. Let me go back to it. Let me see if I can blow this thing up. you see this? It says transmitter baseband. You'll see that it goes from 0 to 10. Up on the top part, you'll see 0, 10, and 20. Let me explain the two switches. How do you get 30 dB? Well, you got to flip this one out of 20 and this one to 10. That will give us 30 dB of attenuation. So if I wanted to do, let's say, 15 dB of attenuation, I would have to click this top switch to 10 and click this switch to 5 to give me 15. Does everybody understand?
Yes, sir.
Kind of crazy. I know, it's just really weird how they did that, but it has everything to do of where they locate the multiplexer and getting it to the baseband. So the cable length is the key. And with the FCC 100 that we used to hook up to the tissers, you would literally have to put approximately 12 to 15 dB of attenuation to get it at 3 volts peak to peak. And this comes straight out of the tech manual. Now, why 3 volts peak to peak? Well, that's the way the equipment works. Normally, when we see coming out of the multiplexer, it's normally 5 volts peak to peak. So you can see why the attenuation would be needed. Next up, we're going to come, and by the way, if you hadn't noticed, the dark lines that you see is how the signal path works. This bandpass filter, it works off of, you have mission bit or mission traffic coming in. Now that's at pseudo NRZ or the CDI that's coming in. One's at 72K to, I think it's 4608, I think, and the other one is like 6.448 meg. So you can see that there's two different frequencies that are coming in. When we hit this baseband filter, we're going to clean off something called 8.5 megahertz. Now, why is that? Well, we'll get to it when we talk about Orderwire. We're going to hit the next summing buffer amplifier, and you'll notice that this is where we're going to combine whatever mission traffic it is, either CDI or pseudo NRZ, and we're going to combine it with our Orderwire. Now, our Orderwire is going to be at 8.5 megahertz FM, frequency modulation, FM. So you got an FM signal and you have the baseband signal all on this together. We're going to go up to a diplexer. What is it going to do? This is where I'd like to call it putting it on a two-way street. It's going to keep the frequencies separate. What does it mean by keeping the frequency separate? Well, I'm giving you a little precursor. First of all, we discussed that down here we have the 72 to 4608K or the 6144K, and we have the 8.5 meg. So we have a lot of items here. When we go up to the diplexer is going to be able to let it go through and go out the rear of the baseband assembly to get to the RF assembly. But there's also something else happening on that line known as a 70 megahertz. You see the 70 megahertz right above the diplexer here? Well, that 70 megahertz is your receive RF. So you got transmit going one way and receive going the other way, but they're two completely different sets of frequencies. And the idea behind these bandpass and low-pass filters is to keep these things separate from getting the 70 megahertz onto our mission traffic line and to keep the baseband from getting onto the 70 megahertz line. That's the whole gist behind diplexers. But we're going to combine them to where they can go out the baseband assembly to the RF assembly. So coming out of the rear of the baseband, going to the rear of the RF assembly, and that's that 2-foot cable we talk about. See the RF assembly here, showing you the tech order coming out of the baseband into the back of the RF assembly, and this is where magic starts to happen. We're going to hit a diplexer again. The hole just behind the diplexer is to either combine them or separate them. In this case, we only want the baseband to go on the transmit side. We want to prevent the 70 megahertz from getting into our transmit side. We want to keep it separate so it can go to the receive side. At the same time, trying to keep the baseband from getting onto the 70 megahertz. Out of the diplexer into this amplifier. Now, if you hadn't noticed, most of
I'm so sorry, sir.
Go ahead.
I'm so sorry, sir. I lost my phone.
Uh-oh. Well,
Yes, sir.
you just got here, right?
Yes, sir. I'm so sorry. I just found it.
Where'd you find it at?
It was under the mattress.
How did that happen? Fall through
sir.
or something?
It fell through the side, sir.
Interesting. We'll talk about it after
Yes, sir.
class here. All right?
Yes, sir. Yes,
All
sir.
right. So what I'm going to tell you is get into your C's and D's or follow through on the slides. This is being recorded, so I'll have that up for you guys when I get it edited and put back onto the RF transmission website and send you a link in the chat. So that way you're not, you can at least watch the front end of this. So we're going to pick
Yes,
up.
sir.
Okay, yes? Questions?
No, sir. Not at all.
Okay. So is that good enough for you on that so you can catch up?
Yes, sir.
Okay, we good to go now? You got everything
Yes,
up
sir.
ready to go? All right.
Yes, sir.
All right, I'm going to continue with I think this is page 5 of your C's and D's. First one being 4. And if you hadn't noticed, if you take a look at the bottom of your C's and D's, it'll say baseband assembly, transmit, and the other one will say RF assembly, transmit. When you get to pages 6 and 7, they say receive, RF assembly, RF assembly, and then it'll say baseband assembly, receive. So that's how you can tell the difference between the two. Now for Loopback, we don't put them in there, but they are on the electronic C's and D's or in the tech order. They're very quick anyway. So just give you an overview. Just follow the bold lines when you're looking at transmit and follow the bold lines when you are in receive. Alright, so we're going to pick up and I'm going to show you this little triangle right here. Anytime you see a triangle, they're normally amplifiers. I've not seen anything different from that. Now they may be a different amplifier than you're accustomed to seeing, but there are differences out there. Alright, so we're going to hit this first amplifier. Now with a 2-foot cable, do you really need to amplify? Class. Hello?
Yeah.
Okay, with a 2-foot cable, you're saying yes, we should?
No, sir.
No, probably not. You're not going to do any... Remember that Rago? When we were talking about receive? You receive signal strength. This is a little bit different. Kind of works like TGC, transmit gain control. This one works a little bit differently than transmit because we're not transmitting yet. But it gives you the sense that if you're using the 150-foot cable, you're going to need to amplify. If you're using a 2-foot cable, you're probably not going to have to amplify. Now, normally when I see a triangle like that, there is something called a compression amplifier. Well, let me explain a little bit about compression amplifiers. Compression amplifiers do 2 things. First of all, it's going to amplify. But if, in the case of the 2-foot cables, since it amplifies, It's also going to do a feedback loop through and sense that it is too much for what needs to be sent for modulation. Hence the word compression. It's going to compress it. Whereas if we had the 150-foot cable, it's going to sense that we've got a very weak signal, and it's going to let it amplify and not compress at all. So that's my theory on it. I'm sticking with it. Bottom line is, normally triangles are amplifiers. So we're going to amplify the emission traffic if need to be. We're going to use the transmit encoder. Remember the RF assembly back here and these encoders? Well, we're using the bottom encoder here, gentlemen. And we're going to send it through the data switch. Now that data switch is very important. Whoa, let's get there. The data switch is very important because it does a couple things. When you are doing the TISR, one of the first things it has you to do before you power it on is to make sure your standby operate switch is in the standby position. Let me give you some background on this. The standby means that you're in loopback and you are not transmitting. If you are in operate and accidentally power that thing up, you're basically transmitting, and anything you're touching at that point has the chance of getting an RF burn. You don't want an RF burn. So always take a look at that standby operate switch, and even tells you in the tech order, check your standby operate switch and make sure it's in standby. What we're doing right now, we're going through the operate phase. In other words, we're transmitting and telling you how it's working in transmit. So the standby operate switch is in operate. So this data switch is extremely important depending on what position that standby operate switch is in. Right now it's in operate, so it's going to let that transmit encoder signal go through. It is binary coded decimal, ones and zeros. We used to teach this back in the day, where we would go through and tell you which one of these, just by putting in a number, we could tell you what the outcome would be at the end of the schematic in ones and zeros. So it's going to let this BCD through, and it's going to tell the phase lock loop what to do. Because the phase lock loop is basically your telling what frequency to operate on. Now, when you get to this VCO, it does a couple different things here. First of all, it's called a voltage controlled oscillator. In other words, the PLL is going to control that oscillator by varying the voltage, whether it goes up or down in frequency. It also does modulations, better known as FM, frequency modulation. You'll notice that underneath of it, it says 7 gigahertz VCO. And then it says after it's and times 2. Let me explain what's happening in that VCO. The VCO is going to put out a frequency range of 7.2 to 7.625 gigahertz. So what have we done? Well, what was the first thing in that basic transmit objective? Anybody remember what the objective was for our basic radio? Somebody try it. Anybody know what the basic objective is, or the objective is for a basic radio?
For a radio would be to transmit and receive beyond.
Okay, we're just wanting to transmit, because I gave you two objectives, one for transmit, one for receive.
Would the first one be modulation?
Okay, you're close. I'm just asking for the objective. Just keep it simple. We'll go through the 3 steps here in just a minute. What is the objective of transmit?
To transmit a baseband to the dissonant.
Perfect. Exactly. So what's the first stage that we do?
That would be modulation, right?
Okay, so what did we just do in that VCO?
We modulated.
Yeah, we modulated it to an FM. What else did we do? Okay, let's continue on. You'll get it here in just a minute. Okay, so we've gone from baseband to IF. That's what I was trying to get at. Baseband to IF. IF being the 7.2 to 7.625 gigahertz. The next stage of this is the multiplier. You're going, well, it's an amplifier. Well, that's very true, but if you know the background of amplifiers, it's going to take that, whatever the frequency is of 7.2 to 7.625, it's going to amplify it. And any time that you amplify any frequency, you generate something called harmonics. Everybody's going, what is a harmonic? Well, our first harmonic is a 7.2 to 7.625. Our second harmonic is from 14.4 to 15.25. Start to see the multiplication on there. And of course it has third and fourth and fifth harmonics on there. What comes after the multiplier? So we've got this signal, we've got, let's say, 5 harmonics in there. We want to keep number 2 because that's our frequency range. And what do we run through? A bandpass filter. What does it do? It gets rid of the first harmonic and the third, fourth, and fifth, and whatever else it can find out there, and eliminate it. So now we have going from our baseband to IF, which is the modulation, IF to RF, which is the up converter. And by the way, it uses that VCO, your oscillator. And then we're going to run it through something called a FET amplifier and bring our signal, which is the high-powered amplifier. So we've done our 3 stages in there. Pretty cool, huh? So we've done our objective. We're getting ready to do the last part of our objective, I should say. So we've gone from baseband modulated to our IF, IF to RF, which is up conversion, and RF amplification, HPA. Now we're running into what we call the branch assembly. Remember we talked about that yesterday. What the heck is that circle with the arrow in? Brownback.
That's the isolator.
Good. So let's take a look at our isolator then. Prevents reflected energy from damaging the power amplifier. Boy, that sounds familiar. Just a little bit more intense, so to speak. In other words, we're saying, hey, this is going to prevent our signal from getting back into our transmit side. And the last thing we want to do is have VSWR coming back. Well, we still have all those harmonics because back here in that FET, it's an amplifier, and anytime that we amplify again, we're going to generate harmonics, and we run into a harmonic filter. So the whole idea behind this is still keeping our original signal, which is the 14.4 to 15.25 gigahertz operating frequency. Because we've generated harmonics, we're going to eliminate them and just let that original signal go through. And what do we run into? A circulator. Again, this is a 3-way. The whole idea behind this is to keep the signals from doing a couple things. It can sense what you want it to do. In this case, if we followed this line going up to the pre-selector filter to attenuator, you'll notice that we are in the operate mode and it is not going to go up into the receive section. It is going to go through the standby operate switch, and then go into another. Well, it's showing you the standby operate switch, and it's going to go into another circulator. This circulator is going to determine the transmit frequency is going to go out the antenna and not into the receive side. The receive signal is going to not go into the transmit side, but go into the receive side. It can sense it that way. And then out through the tisser, dish, waveguide, whatever you want to call it at this point. So that is transmit. We've done the basics. I've shown you the branch assembly. I've shown you the 3 steps for the radio objective. That's about as simple as we can get it for there. And I told you everything that is in the transmit section in Chapter 5 for your TO. Pretty cool, huh? Any questions?
No, sir.
No, sir, not as long as we can use the TO on the test.
Well, you have the tech order, you have the C's and D's, you have a choice
Yes, sir.
between either the paper copies and or the electronic copies. I like the paper copies because I can pull them out and it's right in front of me and they're large. I think they're
Yes, sir.
11.5 by 17, if I'm not mistaken. So they're pretty large, and they have the line of sight where it shows optical versus true versus the radio horizon, as well as the repeaters on there. I think that's pages 1 and 2 and 3, if I'm not mistaken. All right, there's no questions on transmit side. Let's go to receive. Where are we going to start? This is on page, I think, 6 to start with, and then we'll go to page 7 for it. Again, it's telling you right on the front page here of our slide that showing you what paragraph that these guys are on, taking you through the receive section. And we're going to start with the RF assembly because that is where the receive signal is coming in through our antenna. And again, follow the bold lines. We are in operate. There is our tisser, comes in through our dish. First place it's going to go through is that circulator. Circulator is going to let the RF frequencies go in through the bold line. It's going to keep the transmit frequency from going into the receive because that is a passive device with, again, ferrite cores to determine which way is transmit and which way is receive. There's a lot of engineering that went behind this. How they figured that out, I have no earthly idea. These guys are a lot smarter than I have ever would come to fantasize about. So we go through the circulator. We're going to go through the standby relay switches. Again, this standby relay switch is pretty important because it controls a lot of these relays. In this case, we're going to let it go into the receive side of the house. We're going to hit the pre-selector. Let me show you where the pre-selector is on this puppy. Here is your pre-selector. Right there. You're going to adjust this to your receive frequency. Remember, your receive frequency is on the top, not the bottom. So when you see your cut sheet, it will always put the transmit on the top side and receive on the bottom side, but it's up to you to figure out, hey, I got to make sure that I'm putting the transmit frequency in the correct thumb wheels. Receive, thumb wheels, and my dial down here. We have a lot of people that just can't figure out that that's the extra step in there. And by the way, it doesn't tell you to adjust your receive frequency on there. It just says put in your transmit and receive frequencies on from your cut sheet. So that's what the pre-selector is going to do. It's going to filter out most of the received frequencies. The idea is I only want from 14.4 to 15.25. I don't want anything else. This is a pretty big, a wide filter, but in the conditions in Loopback, if you don't have this thing adjusted properly, you're probably not going to get Loopback very good on it. You're going to start to see some crazy readings on your meter. We're going to go through an isolator, and that is the second part of the branch assembly that we've gone through. So if you hadn't noticed, that's part of the branch assembly, which is the pre-selector, and this is your branch assembly. So let me stop here and ask Garcia here, what is the objective of the receive on your basic radio? You remember? No idea, Garcia? Okay, I can see you keying up, but I don't hear you. Does anybody else hear him? You want to answer it in chat? Oh, you have no idea? Well, let me ask Van. Can you tell me what the objective of the basic radio in receive is? Van Hoogstreet? Are you there? Okay, you're typing, which is a good sign. Okay, no one has an idea what the objective is for receive on our basic radio. Let's take a look at, go ahead.
Is it to recover the baseband signal at the end side?
Exactly. Recover the baseband. What'd you do in transmit? Well, we transmitted baseband to the dissonant. If I'm on the opposite side of the receiver, or excuse me, on the opposite side receiving it, I want to recover it now. So that's the whole idea. If you get the transmit down, you should be able to get the receive down. So we've hit the branch assembly. If we take a look at that, what's the 3 stages of the objective in the basic radio?
Is it RF signal recovery?
Okay.
Down conversion?
Okay.
And is it demodulation?
There you go. Yeah, exactly. Keep it simple, guys. I don't know how else to say this, but it's probably one of those things that you're missing. If you keep these concepts simple, you'll be able to pass this test with flying colors. You really will. Keep things simple. Take a look at what's happening in the tech order. You should be able to read it and go, Mr. Mayer said that, so it should be golden. Don't quote me on that, but hey, I do my best. So we're coming out of the branch assembly and we're going into something called a low noise converter. Does anybody know what LRU it is? That's line replaceable unit. It's on the slide there. Let's see if Airman Brownback can tell us. What is the LRU? What LRU is that in?
The low noise amplifier.
No, that's the box it's in. That's part of the card.
Oh, sorry, sir. It's a microwave. I just can't read.
Yes, exactly. All you got to do is follow these dotted lines, and somewhere in there you'll find the LRU. Now, how many LRUs are in the RF assembly?
Two. 5 total.
Nope. 3. 5's in the baseband, 3's in the RF assembly. When I ask you a tech order question, where should you go to?
That's
You cut off there.
Yeah, sure.
Well, yeah, you could classify it as an extract. Yes, it is a TO extract. Yes, but there's only very few missing out of that tech order, which is chapter, I think, 6, 7, and 8. And what's 6, 7, and 8? Those are your intents. Oh, geez, I'm trying to tip my tongue. I can actually see the pictures of it. It's a more of a diagram of what's internal to the radio. I think that's in Chapter 6. Chapter 7 or Chapter 8 has the what's called the breakdown of the whole system and what you can order, and it has part numbers that identify what to order. Because some of this stuff is still troubleshot down to component level. You'll see them when you get out in the field, the older equipment. You'll see that you might have, in fact, we still, if I'm not mistaken, the airfield upstairs in Jones Hall still teaches the 171 and 211 along with the 21, 22s, 23s, and 24s, which are receivers, single channel receivers and single channel transmitters, along with a power amplifier, and most of that is troubleshot down to component level. I think the oscillators and the amplifiers you have to send off. Now, when you come down to the Prick 150s, the 117 Golfs, those, if you find something is broken, you got to send it to depot. So we've gone from down to component level up to depot now. Alright, so we go through the low noise amplifier, which is in the microwave LRU, and here's the first stage of that: signal recovery. We're going to amplify a very weak signal and bring it up to where it's a usable signal to get mixed. We're going to go through something called an image reject mixer. Now, with any mixer, you need an oscillator and you need a RF signal. In this case, our signal that we're going to mix is coming from our oscillator. We tell it what to do from the encoder, and we're bringing it into the VCO, gets ×2 up, cleaned up, and into the mixer, and it mixes with the received signal. Now, let me explain something about this particular signal for your VCO. It has to be 70 megahertz off of the original RF signal. If it wasn't, when you tried to mix your, let's just say, 14.4 with a 14.4 oscillator signal, you get nothing out. You get no way to get the 70 megahertz out. But by doing it 70 megahertz off of the receive signal, you're able to get that 70 megahertz difference. Because when you heterodyne, you get 4 signals. You get the 2 originals, which are coming from the oscillator and the receive, whatever frequency you're receiving. You're going to get the sum, and then you're going to get the difference. So when it comes out of the mixer, we're going to amplify it. Anytime we manipulate the signal, you should see a preamp. We amplify it. We're going to amplify it a little bit more, and that's to gradually bring the signal up, because when you put a signal that's that high up, it has a tendency to get a lot of noise with amplifiers, especially if you over amplify it. We just want to gradually bring the signal up to where we can clean it up again. So by the time we get through this bandpass filter, it's centered on 70 megahertz, and the way they classify this is it's 70 megahertz plus or minus 10 megahertz, which means it goes from 60 megahertz to 80 megahertz. It is also going to clean up all the other frequencies that came in, which is your two originals and the sum. You imagine the sum being somewhere around the 30 gigahertz? That'd be pretty wicked. So it only wants the difference to go through. We're going to go through an AGC IF amplifier, and what's going to happen is the RSL is going to determine how much we need to amplify it based on the received signal level. Remember Rago? There you go. We're going to hit a Diplexer. Again, it's going to keep the 70 megahertz, from getting on the transmit line, and keep the baseband from getting onto the 70 megahertz line. We're going to go out the rear of the RF assembly through the 2-foot or 150-foot cable into the baseband assembly. Again, here's your baseband assembly. We start with, I think this is page 7 on your C's and D's. We're going to take the bold line up to the Diplexer. Again, the Diplexer is going to keep the baseband off of our 70 megahertz line and let our 70 megahertz go through. It's also going to keep the 70 megahertz from getting onto the transmit baseband line too. We're going to hit the cable AGC. Wow. Remember the 150-foot cable? This is where it's going to compensate for. Normally I classify this as a compression amplifier because if you had a 2-foot cable, it probably doesn't need a whole lot of amplification, but it does need a bunch of amplification if you have the 150-foot cable. We go through an IF demodulator. And what does that do? Well, with anything, when you demodulate a signal, it's called a discriminator for FM. Why they didn't put that in there, I have no idea. So it's a discriminator. It's going to pull out the baseband signal as well as the Orderwire signal. Now the Orderwire signal is 8.5 megahertz versus either the CDI or NRZ, pseudo NRZ. We are going to amplify it and send it to a low-pass filter. This is where I like to say caution gets thrown. Caution because not only does it say low-pass filter and says passes emission traffic, it does do that, but not all low-pass filters can filter out the 8.5 Orderwire. It only happens when we get through the 8.5 notch filter does it truly pass baseband. So when you look at the low pass filter, it's going to clean up everything else and in hopes that it will get the 8.5. But if not, here's where your definite 8.5 gets filtered out. So in other words, your Orderwire does not get onto the mission traffic. When you look at this FOGM interface, there is a switch on the baseband assembly. Let me go back up here. Right there it is. There's your GM FO. FO being fiber optics, which I think is the pseudo NRZ, and GM being your CDI. There you go. Tells you everything you know. We're going to go through the attenuator. Now this is not like your other attenuator that goes your attenuator is right here. It only goes from 0 to 10. Not like your transmit, which is 30. This is 10. Why is it different? Well, this one's not, your multiplexer's not right there at the RF assembly. It's coming in from your RF assembly. So if you need to attenuate it, you can. Again, the whole idea is to get it to 3 volts peak to peak. And then when you put it out this connector off the back of the baseband, it will be connected to a multiplexer. So this gives us the receive. This is all where the switch was in operate. So we've gone through transmit, we've gone through receive. I've shown you where the basic radio is there. So are there any questions so far on this? Nope.
No, sir.
All right, let's go to Orderwire. Now, Orderwire is probably the most simplest thing that you can get. It's probably about 3 paragraphs long, and there's some key points that you have to take away from this. So let's get right to it. Well, first of all, what is Orderwire? Orderwire is done either through the handset or headset. Orderwire is our voices being put online so we can go on that 8.5 megahertz and get mixed with the mission traffic. In other words, we're separate. We are that ancillary channel, and we need to operate to find out if there's anything wrong from one end to the other, especially when we're lining everything up. You can see that our order wire starts right here. You can see a speaker that is external, or it's on the actual equipment. But also you have a couple connectors. This one is the baseband assembly, and I think it's the hand set. There is a headset on the RF assembly. So you can connect that up, go through the order wire. Your first place is going to come down into the transmitter subcarrier generator. The whole idea is you're going to take your voice and it's going to go onto and modulate in an FM signal at 8.5 megahertz. And then it's going to hit the summing buffer amplifier, get combined, and then sent up to the RF assembly. Now when it comes back around and gets on the receive side, and this is this top cable here, top part of their slideshow here, excuse me, our C's and D's, you can see we got the cable AGC, the IFD modulator, going into, of course this is where it gets weeded out, the 8.5, but here is where it demodulates the 8.5 megahertz carrier discriminator, and at that point it also blocks the baseband. So only the voice is going to come out, go through here, and go through that connector or the speaker. Now I want to point down here where this test tone oscillator is. It also goes on to this particular system right here. It will come in and act like regular audio and get mixed into the signal to be looped back around. That's what test tone oscillators will do. And you'll be able to hear it. If you have the headset on, be prepared. Do not do the test tone while you have the headset on. It'll blow your ears out. You don't want to lose your hearing at such a young age. So here are some things that the order wire is all about. And you can see where we have the intercom order wire switch in the order wire position. You're going, what? I don't understand. Order wire position. Here you go. Click. Blow this up. You see this right here? It says baseband off, order wire. That's your test tone. Here is the big time switch for intercom and Orderwire. What does that mean? Well, intercom means that you can talk between the baseband and the RF assembly, especially if you got it separated out with the 150-foot cable. Because nothing's more frustrating than have to yell the instructions down to the other side. So this makes it easier for you. If it is an intercom and you go to where you put this switch in operate, you will not be able to talk to the distant end. It needs to be in Orderwire. If you do not have it in Orderwire, you won't talk to the distant end in operate. Now you can talk to each other when you're in intercom and Orderwire, regardless if the switch is in operate or standby. But in order for you to talk to the distant end, this switch has to be in Orderwire. This switch has to be in operate. Let's see. You got 0 to 4 kHz signal. We got the subcarrier generator I just told you about. You've got a test tone oscillator 2.6. That's for your testing. And anytime that you do a test tone detector, you will see on these switches where it says T/T, that's your test tone. Here's another one that says test tone. Here's another one that says test tone. This switch will be either in Orderwire or baseband, and depending on whether you're transmitting or receiving, you should see the test tone light up.
Sir, you cut off for a little minute.
Okay, I'm sorry. Where did you guys leave off at? The picture?
Yes, sir. It's just the screen went black, sir.
Anybody else have an issue with that?
Not on my end, sir.
Okay. Well, let me go through this again for Aaron Robinson here. Okay. I was telling him about the test tone. You see where the test tone light is? Here? This switch has to be either in Orderwire or baseband. Whoa. Well, that could be part of the problem. I just got some really nasty lightning on the end. Anyway, this test tone here, and a test tone light here, and a test tone light here. When you are doing your test tone, you should be able to look at these to determine whether or not you are getting your loop back. That's what those lights are for. Now we're going to look at standby and loopback. When the switch is in standby, okay, when the switch is in standby, look at the path. Look at your transmitter encoder. Remember I told you that data switch is important? Here's your data switch. Notice it's connected to standby. When it senses that you have put your equipment in standby, the data switch stops the transmit encoder from influencing what the phase lock loop system is going to do for your VCO. Instead, it's going to take the receiver encoder and put it in line. And you're going, huh? I don't understand. Well, when you put your frequencies in the transmit and receive encoders, they are approximately 200 megahertz apart. So it doesn't make any sense to put the transmit encoder in line if all I'm going to do is not get a receive signal. So by putting the receive signal encoder in there and letting it go through the transmit line, when it loop back around, because it didn't go out the antenna, it goes through this way now. Most of it goes to the dummy load because you don't want to saturate your front end of the receiver with 316 milliwatts. It'll toast it. So what it does is most of your wattage goes to the dummy load. Some of it will come up, go through the attenuator, because that's what it's going to do. It's going to attenuate the signal down, so you have two different loads there, and bring the signal down to a usable level, and that's where the pre-selector comes into play. So the only time that you see this filter take an active part is when the receive encoder is online. If this was in transmit, in other words operate, this filter would filter out any signal from getting back through to the other pre-selector, because the pre-selector here also selects this pre-selector here. So whatever the frequency is here, it's going to pass the receive encoder here. It's going to block transmit. That's what it's there for. So you can see this loopback comes through here, up, around, it never goes out the antenna, back through. So now I'm able to differentiate between what is received and the 70 megahertz and make everything happen to where I get the loop back. And you're going to hear yourself when you do your checks as far as test tone is concerned, as far as voice is concerned, on your checks in loopback. If it is not in loopback, or if you have loopback and you can't get anything, most of the time your problem is right here. Your pre-selector is not on the right frequencies. Most of the time it'll let it go through, but I've seen it to where it will not work. So that's what loopback does. The key is this data switch, which enables the receive encoder to get onto the transmit line. And there you have it. Passes receive frequency BCD when in standby mode. And that gets onto the transmit line. And of course, the standby operate relays, when you're in standby, it's going to prevent it going out the antenna and loop it back around. I'll let you read these. So we've gone through purpose, operating characteristic, types of traffic, equipment, and signal flow. Any questions on our information today? It's pretty intense for Chapter 5 because we went through transmit, receive in the operate mode. Then we did the order wire, and it can be either in operate or standby depending on what you've got your switches in. And then of course loopback, you're in standby at that point. Is there any clarification that you need on that?